Hello, worldly crazy people out there. My name is Michael. I like wizards and dragons and making games, and let's talk about color grading. So, if you spend a lot of time on the computer graphics side of the internet, you may have seen at some point people talking about these things, these squares, swatches arranged in a grid like this. Sometimes you'll also see them in a linear list, but usually it's in a grid. And you may have also heard people talking about lookup tables, or LUTs, if you want to make it sound like you just got punched in the stomach. We're going to talk about those today. So the main thing that you would use these for is color grading, similar to opening up like Photoshop or whatever and messing around with the color curves. And we'll get to that soon enough. But before we start writing any code, a word about color spaces. So red, green, blue, the color model that you're going to be using by default in shaders is what is known as a color space. If you know how those work, you should be able to dive into this pretty easily. If you don't know how those work, real quick, if you imagine a cube with one corner at the origin 0, 0, 0 and the other corner at 1, 1, 1 in three-dimensional space, you could imagine the each of the approximately 16 million different unique colors that you can display in standard 24-bit color occupying some location inside that cube. You can imagine black is the origin 0, 0, 0, white is the opposite corner 1, 1, 1. Image manipulation software usually envisions them going from 0 to 255, but in shaders we do 0 to 1 to make the math a little easier. There are other color models that exist. HSV is often used in artist software, or HSL depending, because that makes it look a little more like a color wheel. YIQ exists, YUV exists, YCBCR exists. Those are some of the weirder ones that are used for other specific tasks. Anyway, let me make this a little bit bigger to make it easier to see. If you imagine... that might be a little too big. That doesn't quite fit in my screen. But if you imagine splitting up that cube of RGB color space into chunks of 64 on each axis, and if you then take each of the slices, oops, how do I not do that? If you then take each of the slices on the blue axis or the z-axis and slide them around so that they're in a linear and or a square list like this, either into a linear array or a square array, then you have what is basically a lookup table, a color lookup table. And we have now mapped a 3D color space approximately onto a 2D image. Just a note, 3D textures in computer graphics do exist. In GameMaker, we can't access them yet. Possibly in the future in GMRT, which will use a newer graphics API, we'll be able to use 3D textures. But for the time being, we'll pretend that that's not an option. Color lookup tables you often will see arranged in a square array of swatches like this, or occasionally a linear list, like a really long linear array of swatches. The square arrays seem to be more common, and I'm going to use the square arrays in this video anyway, basically because it fits on my screen nicer. Anyway, what you'll do with color lookup tables like this is you will input your original source color in RGB color space into that cube, and you'll take whatever color that you find at that coordinate in the lookup table in that color space, and that will become your new color. And you can use that to adjust colors. If you were to use this lookup table to apply color grading to an image, for example, this is what we're going to use in this video, then the color that you put into it would be the color that you get out of it. It is a neutral color lookup. It's not doing any sort of color grading. If you were to use, for example, instead a grayscale lookup table, so this is basically this image, but the saturation has been dialed all the way down, then you could use this lookup table to apply a grayscale filter to this. If you were to use instead something like this, this is like I affectionately like to call sepia filters brown scale. This would give you a sepia filter or sepia filter. Nobody can ever agree on how that word is pronounced, so I'm just going to say both to piss everyone off. Anyway, you could use this lookup table to convert this image into brown scale. And you could do all kinds of other things. You could take this neutral lookup table and you could just like mess around with you could load it into something like Photoshop. You could mess around with the color curves, and then you could like reduce the red and green and you'll be left with a bluish image. People often use that to do like a nighttime color grading in games or in whatever. Even if perhaps in real life, things don't really turn blue as much at nighttime as much as they just turn, dark. So let's go and have some fun with this. I'm going to close all of these. I'm going to go back to GameMaker. I think I can close the grayscale one too. My sample project is about as simple as they come. So we just have a SPR_photo. We're stretching the definition of a sprite just a little bit, but that's what GameMaker is going to call it. So that's what we're going to call it too. and it's going to be drawn in the draw event of this here object 1. Let's see. Oh, cool. When I like increase the font size in the old code editor, until I like click back into the window, like the position of the text caret and the highlighted line is like all messed up. That's never noticed that before. Anyway, what do I want to do? So the first thing I'm going to do is create a shader. I suppose I should list off some of the things that you're going to want to know before getting into this. You're going to want to know about shaders, obviously. I'm just going to call this shd_lut. You're not going to have to be like a 3D math wizard or anything to do this, but you are going to want to know a few things about. You're going to want to have some experience about using colors in shaders to do things that don't necessarily, at least on the surface, pertain to color. I've mentioned this a couple times. Things like using colors and like palette swaps and stuff. In this case, we're going to be using a color value. Let's go into the fragment shader because we don't care about the vertex shader today. Today we're going to be using a color value. We're going to be mapping it into that RGB color space that has sort of been smeared onto a 2D image, and then we're going to use that to get the adjusted color value. And this part is optional, but we're also going to be using a little bit of random number generation in shaders just to smooth out edges that you might get when you like quantize colors like this. So let's start writing code. So when we draw our image just as it is, you can sample from texture 2D, GM-based texture, v_v text chord. We're also going to want a second texture that we can sample from, and that's going to be uniform sampler 2D. I'm just going to call the samp_LUT, and I think that's going to be all that I use this for right now. We'll get into some more fine-tuned controls over this at a later point. I'm going to, instead of saying gl_frag color equals your v_v color times the sample texture color, I'm going to call this, let's say vec3 source color is going to equal that, and then it's just going to be the RGB of this because we don't really care about the alpha. Generally, when you do something like color grading like this, it will be a post-processing effect after everything in the actual game has already been drawn, and you're just going to apply this to, for example, the application surface. In this example, I'm just going to be applying it to this one single sprite here, just to keep things simple. So again, I'm going to need to figure out where this source color lives in like the 3D cube of RGB color space. I'm going to need to figure out where the location of that color would be in this 2D representation of RGB color space. For example, like white would be down here in this corner, 1, 1, 1. Something like a dark reddish magenta would be something maybe here, over here in this part of the image. Something more like a something more like a light green might be more like here, somewhere in this part of the image. And we need to figure out how to map a simple 3D coordinate into a 2D coordinate, which has been like broken up into each of these cells in this image. And the arithmetic for this is honestly not very interesting. I'll probably breeze through explaining it more than some people would really be happy with, but by the end of this, I'll run it, it'll work, and then you have my permission to just copy and paste once you roughly know what it does and you know why it works and that sort of thing. So firstly, let me define a few, var, that's a GameMaker thing, not a shader thing. Let me just define a few values. So the first thing I'm going to define is going to be my cell count. And that's going to be, that's just going to be 8. So the cell count is going to be the number of cells on each axis in this 2D lookup table here. There's going to be 8 of them. The next thing I'm going to do is float color number is going to be 64.0. And you can't really easily zoom in and count them, but if you were to like zoom in and pixel count, you would see that each of these individual squares inside this greater square is going to be 64 by 64, and in total there's going to be 8 total like 8 squares on each axis, and if you multiply 8 by 8, there are 64 total squares in this image. So we are in effect quantizing the RGB color space from like 256 total possible values to 64 total possible values. You can have higher or lower resolution color lookup tables like this. I will get to that later in the video as well. But for now, this example image is going to be 64 by 64 by 64. Let's see. Next, I'm going to say vector3 index is going to equal our source color multiplied by color number. And I'm going to want to clamp this between vec3 of... Actually, I think I'm allowed to do this with floats. I'm going to want to clamp this multiplication between 0 and color number minus 1. It shouldn't actually ever go below 0 because you're never going to have like a negative color value, at least not in like standard RGB color. So we're going to multiply the source color by the color number. So instead of having a vector3 between 0 and 1, we're going to have a vector3 between 0 and 64. And we're just going to say that the max that it can be is going to be color number minus 1, so 63. And that's just to prevent any weird, annoying, like, bleed over. If you end up with a color that lands, like, exactly on the border between two cells, this is going to end up being a vector3 clamped between 0 and 63. You know what? I should probably just, like, leave this image open because I keep going back to it. Anyway, so I mentioned that this is going to be a lot of, like, annoying, fairly boring arithmetic, multiplication, division, modulo, that sort of thing. And, you can sort of imagine why. So the red-green channel of our color that we map into this into the UVs of this lookup table, they're just going to be like the horizontal and the vertical axes of each of these little squares inside the big square, and that's fairly easy to compute. We're just going to want to like remap each of the color values so that they have a different range. Blue is going to be a little more complicated because for blue we're going to have to actually figure out like which square each of like any given blue value lives in. So like it starts out in the upper left with no blue, just red and green, and then the amount of blue in each square just slowly ascends cell by cell, row by row, until you get to this opposite corner here, which is like maximum blue. And oops, that's going to be like if you add the corner of the cell for each blue value lives in to the UVs of the red and green, then you can get the coordinate which the full red, green, blue color value would live in this UV. And let's see. So I am going to say, let's say vec2 blue index is going to be equal to mod floor index dot blue divided by a vector2, which is going to be composed of 1.0 on the x and the cell count on the y. And is that the correct... Alright, I'm missing a parentheses. I'm also going to want to say mod by the cell count. And that is going to give us a vector2. For those who have never come across this before, by the way, you can generally do arithmetic, some multiplication, division, addition, subtraction on scalar and vector types. Just so if you did this, so a scalar value, a single value divided by a vector, what you would really be doing is you would be producing a vector2 that would have index.blue on both channels, and you would divide that by this vector2. And if you've written a lot of shaders, you probably run into this before. But I just want to say it explicitly just in case. We're going to be doing this a couple times in this video because if I wrote it out like this every time, every line of code would be like twice as long. A lot of the times you'll see it, especially with like multiplication and addition, probably more so than addition and subtraction out in the wild. But anyway, that's that. Anyway, we're going to do a little mod operation on the I guess I'll call it the like quantized blue value, and that's going to give us on one axis the like the horizontal cell that the blue value lives in, and on in the other axis it's going to give us the vertical cell. So whatever that happens to be. Anyway, next I am going to say, let's say another vector2, which is going to be a LUT, the lookup table UVs. So this is going to be the final UV coordinate, where we're going to add the blue index into the red-green index. And that's going to be a matter of index.rg divided by color number. And we are going to add the blue index here, and then we're going to take this entire term, this entire expression, and we're going to divide that by the color number. I'm sorry, not the color number, the cell count. Like this. All right. And this is going to take the blue index. It's going to add it to the UVs where the red green lives in each square, and then you're going to divide that by the cell count to get you back to a range of 0 to 1, which is where you like your UV coordinates to be. I wish I could say that there's probably a matrix multiplication trick that you could do to do this transformation into, like, from color space to UV coordinates like this, but I don't think there is, because this isn't a linear transformation, unfortunately. So instead we're just going to be stuck with this gross, stupid looking math. Anyway, so this is going to be our coordinate that we can feed into a texture 2D function into the this sampler over here, and we can say let's say vec3 output color is going to be texture 2D. We're going to sample from samp underscore LUT. Like this, our coordinates is going to be LUT UVs. And then once everything is said and done, we can say GL underscore frag color equals a vector 4 composed of the output color and 1. I'm just saying 1 here so that it's a transparency of 1. Again, usually when you do this, it's going to be on like the final frame buffer, the application surface, as a post-processing effect, so you won't really be looking at alpha. You could use the alpha of the source color if you want to only apply a color grade to like a specific sprite or something that does have transparency, but I'm not going to go there. Anyway, the next thing I'm going to do to actually make this be used in GameMaker is going to be to shader set SHD LUT. We're going to shader reset when we're done. I'm going to want to save our sampler. We're going to want to get a reference to shader get sampler index. That's going to be SHD LUT, and the sampler is going to be the one that we defined in the shader. And then we can say texture set stage. The sampler ID can be the one that we just fetched from the shader there. The texture ID can be sprite get texture. I have not actually added the lookup table to the GameMaker project yet, so let me actually do that. Yeah. Let's import that sprite. I'm also going to want to set this image to a separate texture page so that we can actually make use of the UVs from 0 to 1 when we sample from it. So I'm just going to go into texture settings and check that box. And let's see. I guess I'll full screen this too. Sprite get texture, SPR, LUT neutral, step image 0. And that should be our color lookup table. All right. If anything goes horribly wrong, something went horribly wrong. What went horribly wrong? Oh, I want this to be .rgb because we're taking, this is going to return a vector 4, and I want to assign that to a vector 3 that basically ignores the alpha. That wasn't horribly wrong. Let's just say that's like mildly annoyingly wrong. Anyway, so this is a neutral lookup table, and we do indeed basically have the same image. It's going to be coming out of the lookup table pretty much the same as it went into each of the individual colors in this image. So it's not going to be exactly the same, and if you look at the dimensions of this color lookup table, you might have an inkling why that might be. So there are a total of, if I bring up the Windows calculator, 512 by 512 times 512 colors in this image, which is going to be 262,144 total colors. If you multiplied the total number of colors that you could store in a 24-bit RGB image, you would get something more like this. And this is significantly more than the number of colors that are stored in this lookup table here. And that's if you were keeping score earlier when I said how many colors are in each slice and how many like slices are in the full image, you might have noticed that doesn't add up. You can have a full color lookup table if you'd like, and that would be this number. And if you take like the square root of it, it'll be 4096 by 4096, and that's going to be a huge image. Those do exist. If you're taking a color lookup table and applying it to like the film industry for color grading in a movie or something, you would probably see a full-size lookup table like that. But that's going to be a little bit overkill, at least for this demonstration. But the point of all this is that we are slightly quantizing each of the colors for like a very, very minor posterization effect. And if I were to, in fact, take this, let me duplicate this neutral lookup table and like, let me say neutral reduced is what I'm going to name that. And if I were to just go and just resize this down to like from 512 to like 64 by 64. So that basically each color is put into like a bucket of 8. At least on the red-green. Blue is still going to get a little more definition there. We could run this again with LUT neutral or reduced. And that is going to crush the colors in this image a lot more. That didn't do it. Did I use the wrong one? Okay, actually, you know what the problem turned out to be? It's not that, like, it wasn't working. It's that, like, my camera that I took this picture with is not, like, actually all that good. So the colors turned out to be a little bit smeary anyway. Let me decimate this further. Let's reduce this further to, like, 32 by 32. And now we're really going to be crushing the red and green in this image. And that should make the problem a little bit more apparent. So now we can indeed see that the number of colors in this image really is, again, it's sort of like half of a posterization effect that you would get just by quantizing colors. Anyway, the point of all this is that you will lose a little bit of color information inside a 512 by 512 lookup table like this, but 512 should be enough definition in the colors that you're not like losing a lot. And
Hey.
If you wanted to use a bigger one, feel free. Just make sure to update the cell count and the color numbers in your shader accordingly. Have it behave correctly. Let's go and stop using that reduced lookup table like that. So I'm gonna start adding a few more. Let's add our grayscale and our sepia lookup table images here. I'm just gonna go and make sure to stick both of these on their own separate texture pages so that we don't have any funny business with the UVs. If I were to go and use the grayscale lookup table for this, we have a black and white image just without writing any different shader code, just by plugging in a different lookup table. If I were to use the sepia one, I think I said sepia last time, let's call it sepia this time. We're going to get a brown scale version of the image. I don't think this is exactly sepia, for the record. I was kind of in a hurry when I generated these, and I just kind of like smushed around a bunch of color curves until I got something that looks sort of like old newsprint. But anyway. So another fun thing that you can do is you don't have to, like, you can use a, instead of using exactly the color that you get out of the lookup table, you can have a blend of the original color, or you can even have a blend between between like one color lookup table and another if you want to transition between two for different various effects. Let's see. I'm gonna say uniform float U LUT strength, and that's gonna be a value between 0 and 1, and we can go and just fetch that uniform. Just fetch that uniform from the shader, and we can shader set uniform float. And we can set that to like, if you want a value between like 0 and 0.5 or so for 50%. So we'll make this like half sepia or half grayscale if you like. And then instead of saying our output color equals exactly what you get from here, we can say, let's say, I did it again, vec3 LUT color equals this, and our output color can be mix, so we're going to lerp from our source color to our lookup table color, and our lerp factor, our mix factor can be that uniform, the lookup table strength, and this is going to give us 50% whatever the last sprite I was using for the lookup table was. So 50% sepia. All right. This is maybe not like old newsprint from like the 1920s color, but maybe like sort of old newsprint from like the 1970s color. And then something else you might want to do is to like do the same thing, but to transition between two lookup table samplers. I'm not going to do that. I'm going to say if you want to do that, that's going to be your homework. It should be pretty easy to do that if you've been able to follow along so far. Lastly, and this is definitely optional and something that I think not everyone's going to like, but some people might, so I'll include it anyway. So if you did use a very reduced color lookup table, and if you got something that looks like this, and there's like visible quantization, or even if you're using a bigger one and you have areas of high contrast and you get a little bit of banding, just rather, if you have an area of low contrast and you have a little bit of visible banding that you want to get rid of. I mentioned at the beginning that we'll be going a little bit into random number generation and shaders, and to do that, let me define first a float. Tolerance is going to be 1.0 divided by 255.0. So this is basically going to be like an inverse bit, so to say. And we're going to be using a little bit of arithmetic to generate a random color. Alright, I definitely messed that up the first time I wrote it out, so let's try it again. So we're just going to generate a random number based on the v_v texture coordinate. I made a video on random numbers and shaders a while ago. It's not as easy as just calling like a random function the way it is in like CPU programming. You're going to have to write a random function yourself, and the way that it's generally done is to just like take a let's call it a seed value of largely random numbers. The ones that I used in my test project were like 8-point random garbage and 9-point random garbage, and this is going to be, let's say, call this float seed, and we can use this to generate a random number from each texture coordinate by saying sign of the dot product of the texture coordinate UVs against that random seed. This is going to give us a value between -1 and +1. If we were to multiply this by some large number to like break up the periodicity a little bit, we could have a random number between like -20,000, whatever that is, and +20,000. And if we want a number between 0 and 1 fract, we could just take the fractional part of that. And I can multiply this by the tolerance that we defined earlier, and this is going to take it from a range of like -1 to +1 and map it onto a range of like negative inverse bit to positive inverse bit, whatever I called that. And then we can go down onto the output color and add that random variation, that random number onto it. If we do this, we're probably not actually going to see much. So if I run the game now, it still looks pretty much like it did before. You might want to increase the tolerance just a little bit, like add a random tolerance of 5, a random number between 5 out of 255 to each color, and that's going to add a little bit of like random noise to every pixel, so that the hard edges of contrast are broken up just a little bit. This lookup table is like too it doesn't have the resolution. It doesn't really help. Be wary of this. You can, if you make your tolerance too high, you can get visible noise on like surfaces that you don't want it on. So if I were to like zoom in on like this shed door here, it now looks like you have bits of random noise. And it seems that the random seed that I picked for this isn't perfect, because we do actually have like patterns in it. So that's the whole thing. Depending on like what your seed value is, if it's not random enough, you can like have the output result not look random either. But won't get into that now. I'm gonna knock this back down to like, let's say maybe 2.5 or so. That should be enough random variation. You can also, by the way, instead of adding this onto the output color, you can add it to the input color, so to the source color like this. But that probably... I feel like that probably won't turn out as well. Especially if your random tolerance isn't ever, like, greater than, like, the difference between quantization levels in your image. So if you have, like... So, like, if you have a color, and it maps to, like, here, where my mouse cursor is in the lookup table, and if you add just a tiny random amount, it's still going to mostly be within that, like, that random color, that one same color, when you sample from the lookup table, and you won't see very much, like, noise breaking up the effect, if it's all going to map to the same color anyway. So for something like this, you might want to go with a bigger tolerance value, so maybe 10 would be a little bit more warranted there. Alright, it still looks extremely quantized, but at least it's not like a bunch of hard contrast edges. I don't know. Maybe that's better than what we had before. Maybe it's worse. It's up to you. You don't have to use this at all if you don't think it's necessary. This video has been going on for a really long time. I think I'm going to end this off here. My name is Michael. I like Wizards and Dragons and making games. If you want the code for this, look for the GitHub repository down in the description of the video. Feel free to copy and paste this code, because it's not very interesting and it's not, like, incredibly ingenious or anything. It's just a lot of arithmetic, although you might want to organize it a little bit better than I did in this video to make it easier to use, but whatever. You should all go check out Wizarducks and the Lost Hat, which is one of the games that I like to work on when I'm not doing YouTube stuff. Link to the Steam page can be found down below. I like to post videos on weird stuff you can do in GameMaker, so if you like anything like this, shader stuff or weird 3D stuff, feel free to subscribe. I hope you all found this useful, and I will see you all later. Special thanks to Zenjamin, Squarecrow, Spy Die Games, Manta Ray, GameMaker, GameMart Indie, Edward Holt, and DJ Gibbles for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.